In section 2.2, we spent quite a lot of time discussing permutations. So just to remind you, I've put the definition of a permutation here. And one of the key things about a permutation is that the order of the elements matter. And also just to remind you, we worked out that if we have an n element set and we want to choose k objects, then the number of arrangements of those k objects is given by n factorial over n minus k factorial. But now we want to consider the case where the order of the elements doesn't matter. We're just interested in knowing, for example, how many 3-element subsets we can pick from a 6-element set, or something like that. It's worth thinking about what kind of problem in real life this actually solves. Well, suppose there's a class of 25 students and the teacher wants to pick 3 students to do a group presentation the following week. How many possible groups are there? Now, the order of picking the students doesn't really matter, so we can't use our permutation idea. However, there are similarities, and we're going to see that the work we've done on permutations is going to help us solve this kind of problem. We're going to start with an easier problem. We're going to take the set A, which has 4 elements, A, B, C, and D, and ask the question, how many different 3-element subgroups does A contain? Just to be clear, we're thinking about subsets here, so we don't care about the order of the elements. Well, if we do a little bit of thinking, we can work out that the possible 3-element subsets are ABC, ABD, ACB, ACD, and BCD. And there are no other subsets that we could pick. So these are our subsets. And we might wonder, how does this relate to the permutations that we could create? So we know that the number of permutations we should have is 4 choose 3, and if you work that out, you'll find that it's 4 factorial over 4 minus 3 factorial, and that gives us 24. And we can further break this down and see that for the set ABC, we have 6 possible permutations. We know this should be 3 times 2 times 1. And you could work those out. And in fact, we have 6 permutations for each of those, and when we sum them all together, that gives us our 24. So the question is, where did these 4 subsets come from? Are they related? Well, it turns out that they are. So we're going to introduce a little bit of terminology. We're going to let A be a set with cardinality n. Then the number of k-element subsets, where k is some number less than or equal to n, is given by the binomial coefficient. And just as we had notation for permutations, we have notation for binomial coefficients. The binomial coefficient is represented by this symbol over here. And it represents the number of combinations of n objects taken k at a time, and is read n choose k. So we're thinking of n as the overall size of the set, and we're choosing a subset of size k, and we want to know how many of those subsets of size k can we pick. And if we think about what we saw in the previous example, we saw that we had 24 divided by 6. This was our number of permutations. This was our permutation of 4 choose 3. And then we had to divide through by 6 to get rid of all the duplicates given by permutations of the same subset. And with a little bit of thinking, we realize this 6 is probably 3 factorial. So using that idea over here, we can get that the binomial coefficient formula must look like this. It's got to have our permutation formula, and then we're going to divide through by k factorial. So that's a rough way of thinking how we could derive this formula. So let's go back to our question. We want, from a class of 25 students, we want to pick 3 students to do a group presentation. Well, let's see if we can use our formula. We have n choose k, and this must be 25 choose 3. So if we use the formula, that's going to be 25 factorial over 25 minus 3 factorial, and then we're going to divide that by 3 factorial. Simplifying this, we've got 25 factorial over 22 factorial times 3 factorial. And we can use our simplification formula to say, well, 25 factorial is really 25 times 24 times 23 times 22 factorial all over 3 factorial times 22 factorial. Cancel those. Then we're finally left with 25 times 24 times 23 over 6. And you could put that in your calculator. One thing to note is that our group of 3 students who gets picked is called a combination rather than a permutation. So we talk about combinations where order doesn't matter and permutations where order does matter. Let's look at another problem. So here we're assuming that an evenly balanced coin is tossed 5 times, and we'd like to know in how many ways can 3 heads appear. So we can think about this as a combination type problem because order doesn't matter. We're just interested in how many times can we get 3. So reading through, we've got our n. We're going to throw the coin 5 times, so that's n is equal to 5. And we want 3 heads, so our k is equal to 3. So we compute 5 choose 3, so that's 5 factorial over 5 minus 3 factorial divided by 3 factorial. And if you simplify that, you will find that there are 10 ways in which 3 heads can appear. And it's probably worthwhile at least once to just plot out what those 10 options are. It's worth thinking about the extreme cases of our binomial coefficients. If, for example, we might want to see what is n choose 0, well, there's one way of choosing a combination of 0 elements from a set of n. In addition, we might think about choosing a combination of n elements from a set of n, and we see if you have n elements, there's only one way you can choose a combination of n. So while we could compute these values from the formula, it's useful to just think about these logically. They come from where we expect them to. So next we're going to talk a little bit about Pascal's triangle, which is not explicitly mentioned in the textbook. What is mentioned in the textbook is the binomial theorem, which you can look at if you're interested. But Pascal's triangle gives an introduction to the idea. So Pascal's triangle is a triangular array of the binomial coefficients that makes computation of these coefficients quick. So how does it go? Well, we're going to have a row of our triangle for each of the possible sizes of the set. So we can have a set of size 0, a size 1, 2, 3, and so on. So now if we have a set of 0, then we only have one option. There's only one way of picking 0 elements from 0. Now we're thinking about a set of size 1, and we have two things. We can either pick 0 elements, or we can pick 1 element. And again, each of those options we only have one. Now we're thinking about a set of size 2. We can pick 0 or 1 or 2 elements, and we want to think about how many options. Well, if we're picking 0 elements, we know that 2 choose 0 is 1. And on the other side, if we're picking 2 elements out of 2, we only have one way of picking them. And the trick with Pascal's triangle is that this element here, which tells us how many ways we can pick one element from a set of 2, is given by adding the 2 entries above to the left and the right. So we say 1 plus 1, and that gives us 2. And you can check if you want that 2 choose 1 is equal to 2. For n equals 3, again, on either side of the triangle we've got a 1, and now we've got 2 elements in the middle. And again, we calculate these by looking at the elements above to the left and the right and adding them. So we've got a 3 there, and then we've got a 2 plus a 1, which gives us a 3 there. And again, you should just check to make yourself feel comfortable that 3 choose 1 is equal to 3, and that 3 choose 2 is equal to 3. So just to be clear, this one over here is 3 choose 0, this 3 over here is 3 choose 1, this 3 over here is 3 choose 2, and this one over here is 3 choose 3. And you could keep going and calculate Pascal's triangle for n equals 4. Have a look on the internet if you're interested. So this just gives you a quick way of calculating some of the binomial coefficients. As I said, if you're interested, you can read section 2.4.2, which covers the binomial theorem, which gives us a formula for expanding polynomials of the form x plus y raised to the n, where n is some non-negative integer. And it turns out that the coefficients of the expansion are the entries from Pascal's triangle, and hence the binomial coefficients. So the binomial theorem looks something like this. And if you expand it out into a triangle, where we're looking at n equals 0, n equals 1 for the coefficient of x plus y, you'll notice that our coefficients mimic the coefficients from Pascal's triangle. So feel free to read that, but it's not going to be tested in this course.